Hey everyone, and welcome. Today we're diving into something that's pretty much invisible, but runs our entire digital world: databases. We're going to trace their whole story, from what were basically digital filing cabinets to the massive, powerful cloud systems we rely on today. So let me just start by asking you a question. Think about every single thing you do online. That photo you just posted, the song you're streaming, that thing you bought at 2 in the morning. Where does all of that stuff actually go? I mean, it has to live somewhere, right? It's not just floating out there in the ether.
Well, the answer is actually really simple, but the scale of it is just mind-blowing. It all lives in a database. And these are not your grandpa's filing cabinets. They are the living, breathing heart of the internet. Every click, every like, every single message, it's all stored, sorted, and then retrieved from a database.
So how in the world did we get here? Here's our game plan for this explainer. We're going to start with the original blueprint for databases. Then we'll learn the language they speak. We'll see how they keep all that information organized, then witness the moment everything changed with the big data bang, and finally, we'll step into a totally new reality, a world without tables.
First things first, the blueprint. Imagine trying to build a house without a plan. You just have a pile of wood and nails, total chaos. Well, early on, people realized information had the same problem. They needed a strict, logical structure to make any sense of it all.
To really get this, there are two key ideas you need to know. The first is the schema. You can think of the schema as the architect's blueprint. It's the set of rules that defines what the data is supposed to look like. Then you have the instance. That's the actual building, the live data at any given moment. So the schema is the plan, and the instance is the reality.
For a very long time, the most popular blueprint by far was the relational model. The best way to picture it is to think of a perfectly organized library. Every single piece of information has an exact spot in a table, made up of rows and columns, and all the connections between those tables are strictly defined. There's absolutely no room for ambiguity.
And it's this simplicity that makes it so incredibly powerful. Just take a look at this basic users table. Every row is a unique person, and every column is a specific piece of information about them: their ID, their name, their email. It's clean, it's structured, and it's totally predictable.
Okay, so you've got this perfectly organized library full of tables. But how do you actually find a book or add a new one? You can't just walk in and start browsing. No, you have to speak the language of the librarian. And in the world of databases, that language is SQL.
Now, this language isn't just a random set of commands. It's built on an incredibly solid foundation of rules. A computer scientist named Edgar F. Codd basically came up with the commandments for data, principles that make sure everything stays consistent and trustworthy. This idea of data integrity is the absolute bedrock of the entire relational model.
And talking to the database really just comes down to a few core commands in SQL. If you want to ask questions, you use queries. If you want to add new information, you insert it. Need to get rid of something, you delete it. And to change what's already there, you update it. It's a very direct and very powerful conversation.
Now, having a good structure is great and all, but data can still get really messy really fast. You could accidentally list the same person twice, maybe with a slightly different spelling. To prevent that kind of digital chaos, designers use a special technique called normalization. Think of normalization as a deep cleaning process for your database. It's all about carefully organizing your tables to get rid of any and all repetition. The goal is super simple. Make sure every piece of data is stored in only one place. That's it. It keeps things efficient and makes sure the data is reliable.
And trust me, this isn't just about being tidy. If you don't normalize your data, you are setting yourself up for some serious problems. Let's say a customer's address is stored in 10 different places. What happens when they move? You have to update all 10 of those records, and if you miss just one, boom, you've got conflicting information. This leads to all sorts of errors and violations that can completely corrupt your whole system.
For decades, this relational model was king. It was stable, it was reliable, it powered pretty much everything. But then the internet exploded, and all of a sudden the neat, tidy rules of that old world just couldn't keep up with the pure, unstructured chaos of modern data.
I mean, just look at this chart. It really shows you the sheer scale of the problem. The amount of data being created went from something manageable to something, well, astronomical. The strict ordered tables of the relational model just started to crack under the pressure.
This new era became known for what we call the 3 V's. First, there was volume, just staggering amounts of data. Then, variety. It wasn't just neat rows and columns anymore.
It was messy, unstructured stuff like photos, videos, and social media posts. And finally, velocity. The incredible speed at which all this data was flooding in. It was relentless.
To handle all this, we needed a whole new approach. That approach was MapReduce. Instead of relying on one giant, powerful computer, the idea was to spread the work out. Think of it like a huge group project. The map step is like breaking the project into thousands of tiny pieces and giving one to each person. The reduce step is when everyone brings their work back and you put it all together to get the final answer. It was a brilliant way to tame the data beast.
This new reality forced a complete rethinking of what a database even was. It was time to imagine a world that existed beyond that rigid table structure. And this was the beginning of what we call the NoSQL revolution. And this slide really nails the huge philosophical shift. Old-school SQL databases were rigid and they scaled vertically, meaning if you needed more power, you had to buy one bigger, more expensive server. But NoSQL databases are flexible, and they scale horizontally. You just add more cheap computers to the network whenever you need them. It was a total game changer.
And NoSQL isn't just one thing. It's a whole family of different database types, each for a different job. You've got things like graph databases, which are perfect for mapping out friend networks on social media. You have document databases, great for flexible product catalogs on shopping sites. Each one is a specialized tool built to solve a specific big data problem.
Really, NoSQL was built for the cloud. Its ability to spread data across tons of different machines makes it the perfect engine for the massive apps we all rely on every day. From our social networks to our streaming services, this is the technology that powers the modern web.
And the scale we're talking about now is almost impossible to imagine. We're talking about trillions of data points being processed by these new systems every single day. All of that is working behind the scenes to give us the seamless digital experiences that we now just take for granted. Which brings us right here, to the end, and to one final thought. We've gone from these structured tables to incredibly flexible documents, from a single computer to the entire global cloud. But this flood of data, it's not slowing down. It's only getting bigger and more complex. So that leaves us with one question. What comes next? What will the next database revolution look like?